Hi all, I created this video as part of the solution architecture series. So the concept I discuss here can be applied while designing security for any solution. I would like to take an architecture as an example and show how security architecture is overlaid on the architecture. Here is a simple adaptation of an architecture of a multi-tenant SaaS platform. I worked in for an insurance company, and we looked into a huge insurance problem and we broke it into smaller subdomains. We adopted micro frontend design. The idea was one team owns one subdomain, a bounded context or boundary, including the UI backend or backend for the front end layer or the BFF layer, domain layer, and the database. The web application was a composition of features owned by different teams. Each team maintains their code base, they maintain their DevOps pipeline, they do their design, and so on. The communication from UI to BFF and from BFF to the domain layer was via APIs. BFF and domain are microservices based on a Spring Boot, and only corresponding domain API has access to the corresponding database. The east-west traffic, such as between two domain microservices, was event-driven. Since this was an insurance domain, so subdomains were program, policy, terms and conditions, and so on. Sometimes the BFF layer seemed extraneous and it was degrading the performance, but from security perspective, we will see this is a good architecture. When building a secure system, I generally keep three principles in mind. First is complete mitigation. That is, every access to any resource must be checked for authorization. So first check every request is authentic, request is not modified, and it does not contain any malicious content. We want to know who made the request, and the user is not an adversary or not a man in the middle. We also want to know the user is authorized to make the request. Lastly, we log every request so that we can trace back and we can play back the request. Second principle is separation of privileges. Take computer system as a whole, split it into modules, and give each module the least privilege that it needs to do its job. And by providing it the least privilege, hopefully if that module gets compromised, it can't really do much damage because it runs with not much privilege. The third principle is build resilient system. That is, think about how system can handle any error, any failure, any type of attacks. How system can keep working in such situations. For example, if the backend microservice is down, then what is the UI behavior? Think of all those things. What if one microservice gets hacked? Then how other microservices then keep on working? The application which I'm talking was designed such that it implements those design principles. A user cannot access the application without login. When user log in, they are assigned a role that defines what they can access. If user has access to the program MFA, then user from the program MFA can make changes in the program details or even delete the program, depending on what type of access user has. Program MFA sends commands accordingly to the program BFF, which sends requests to the program domain. Only program domain has access to the program database to perform updates. It may be sometimes required to display some policy details on the program screen. So program BFF has get access to the policy domain API, and BFFs can do orchestration, but they only have get access. A user can navigate or access any MFE only if user has access to the MFE. User can only update policy from the policy MFE. Only policy MFE can send the update delete request commands to the policy BFF, and only policy BFF can send update requests to the policy domain API. No other BFF can send a policy update request to the policy domain API. The layers we define, those layers enable us to define layer security and different levels of security at each layer. At the UI layer, user is first authenticated and given a role or assigned to a group, and the group has a role, and which is later, this group and roles are later used to determine what user is authorized to do and what user is not. Authentication and authorization check happen at the UI layer. At BFF and domain layer, user is only authorized to perform a CRUD operation on an entity if user has the right claim. That is, user is authenticated and user has the right role, the role that is authorized to perform the operation. For example, user can only access account details by account ID if user has admin role. Additionally, if it is a multi-tenant application, then check user is only allowed to access the data belonging to the tenant user belongs. Usually, the tenant ID can be part of the token that is provided when user is authenticated, and it is included in all the subsequent API requests. The rows in the database also have tenant ID. The two tenants' IDs can be compared for authorization at the domain layer. As we move down the layer, the granularity increases. Note, a method level check provides user access to all the objects of any particular type. For example, a user admin role will have access to the account object or all the rows in the account table in the database. Whereas at the MFE layer, we check the user is authorized to access a particular module. Now inside that module can be many classes, and the user authorization to those classes can be checked at the BFF or the domain layer. But what if we want to do more granular check? That is, for example, a user can access few accounts as read-only, and user can access few accounts as read-write, and maybe user doesn't have permission to access some of those accounts. Those kind of granular checks, or even more granular checks. For example, user has access to the account row, a particular row in the table, but user can edit only few fields, and user rest of the fields remain read only for the user. So those kind of checks or those kind of configurations we can do at the database layer. I have used Spring ACL to implement such authorization checks in the DB tables, but there can be some other way also, based on customer ID, based on some information we can keep at the database level, which we can use in the domain layer to check the authorization checks. As we go down the layer or deeper in the layers, not only granularity increases, but also the security becomes more decentralized. Because as we see at the UI level, we have a central authentication and authorization service. So user is authenticated once given a role, whereas down as backend in the backend where are multiple microservices. So each microservice is also doing the authorization checks. So it's becoming more decentralized. Authentication and authorization are the first and the most important line of defense for the application. User enter the credentials, and those credentials are sent to the authorization server. And if user credentials are valid, then authorization server will return a token such as a JWT token. In subsequent requests, the token is included. The microservice which owns the resource A can ask authorization service to validate the token and also check user is authorized to access the resource. This authorization service can be custom built in Java or .NET or some other language, or maybe using some framework such as a Spring Security, or maybe it can be a ready-made tool like Okta or Auth0. It can be optimized. This authorization check can be optimized so that microservice itself can validate the token and do the authorization checks by itself instead of invoking the authorization service and thereby reducing one API call. But for that, microservice will have to include some SDK, which will be provided by the authorization service, like a library. We can manage all our services within one boundary, and we can think that all these services are like one layer. But still, we can do layering among those services based on some criteria, and that criteria we can define. For example, we have some services which are directly invoked from the outside the boundary, and there are other set of services which are internal, which are only invoked by the services within the boundary. This way, we can say we have two layers of services, even though these all services are deployed inside one Kubernetes cluster. We can design such that the external services receive the request from outside, do the end user authorization check, do orchestration if needed, and route the request to the correct internal services. Internal services may be following model-driven design, rich in domain knowledge and business logic. They have database access. And knowing that they are the second layer, they can avoid end user authorization check. Instead, they will do service to service authorization check. That is, that they will check the service which is invoking them is authorized to invoke them. The external service receives a token, for example, a JWT token in the request, and it can do a fine-grained authorization decision on the basis of the caller context information available in the token, such as whether the user is allowed to invoke a particular HTTP method. The token is provided by the Central Authentication and Authorization Service, which can be Okta or Auth0 or something else. If internal service also want to do such fine-grained authorization decision, if needed, that is on the basis of the caller context information, a simple way is to propagate the token received by the external service to the internal service. Note, this is different from service to service authorization. Service to service authorization can be handled at the infrastructure level, such as we can have a firewall in between. We can open some particular ports for the internal service, or we can delegate it to some infrastructure framework, such as if we are using service mesh with Kubernetes. But if internal service wants to know the caller in context is authorized to do some read or write data changes, then it needs the token. We can make authorization decisions in each microservice, but there is a drawback. We will have different teams and people managing those microservices, and they should all understand the security features of using the programming language framework, implement it correctly in their microservice, and they should understand the access control policy and expected permissions for a role or a group. That is the drawback of using a decentralized security. Whereas we can overcome this by building a common library, and we can ask each microservice to include that common library in their microservices and then use it for the authorization decision. But still those method level authorization configurations are still manual, and someone has to review them centrally for all microservices. So that all microservices are behaving in the same way. Alternatively, we can have an authorization decision centrally if we are using an API gateway pattern. This API gateway can be custom homegrown, or it can be ready-made like AWS API gateway. For example, the API management gateway acts on the behalf of the API, and there is a access token between the calling application and the API gateway. API gateway will receive the token and it can validate. So same thing which we are doing inside individual microservices, now we want to do this centrally. Remember, API gateway will also work with some old systems which might not support the newer token formats like a JWT token. And even if you are using a serverless architecture, this API gateway will work fine. So a simple, let's assume a simple architecture where we have an AWS Lambda function that handles business logic. The data is in the DynamoDB, and there is an HTTP API using API gateway that handles the requests and routes them to the Lambda function. Authorizers are defined at the API gateway layer. Authorizers are services that allow or restrict an API access to the client based on the several possible criteria, such as user is authenticated, user has permissions, the IP address is fine, and so on. JWT authorizers are a type of authorization which use JSON Web Tokens to provide access control to your API endpoints. Once configured, the request to your API will require an access token that the authorizer will validate. Note API Gateway does not serve as an identity provider and does not issue tokens itself. The tokens are issued by an authorization service, which can be again Okta or Auth0 something. But we have just one central JWT authorizer who is doing all the authorization checks. All the access control policies are inside the single JWT authorizer. I worked as a mobile banking architect for a large bank, and the architecture there was that they had multiple gateways. The mobile banking team managed the mobile app and its backend, which we can say was the edge layer or the experience API layer. The mobile team had developed a custom mobile gateway in Java and Spring. They were managing security through a combination of features available in the mobile operating system and in the backend inside the mobile gateway. Whereas each domain service, the core domain services were separate physical infrastructure or maybe separate virtual machines. And each domain has its own API gateway. And each domain was doing a fine-grained checks at their own API gateway level. Whereas, yes, the domain API gateway was checking the service-to-service authorization, whereas the mobile gateway was checking the end-user authorization. When one service invokes other service, it uses an access token, and this token is different from the token received from the user request. So the service to service authorization token can be different from the token we receive from the end user. If we deploy two layers of API separately, then we can add API gateway between the two layers so that we have, for example, two API gateways. One is for the external facing services, another for the internal facing services. So on few slides back, I shown an architecture where we had external services and internal services deployed inside one Kubernetes cluster. But now actually I'm saying that we can also deploy them separately in two different clusters. We can put API gateway between the external services and internal services. And whereas the first API gateway checks for the end user authorization, the second API gateway checks for the service authorization. After the external APIs or the API gateway or the external APIs has successfully validated the token received from the caller, the external API obtains an access token for the internal core services. This access token contains the context of the external API, which is the calling API now, and and it can invoke the core service. The caller microservice, the calling API, which in this case is external services, can obtain the token by invoking special security token service using its own service ID and password, and then attach it to the every request it sends to the internal core services. What I was trying to do in showing all those examples was that okay, uh, we have an architecture and we are trying to understand how we can apply security to it. Uh, what we are actually doing is a threat modeling. So we gain an understanding of an application, how it interacts, how external entities will access our resources, the layers of architecture, the entry points and the exit points, the assets and resources that we are protecting, and the access rights or privileges required at each entry point to read or write resources. We can collect all this information and draw a data flow diagram. There are standard notations for data flow diagrams, but it's up to you how to use them. But what we want is we want to visualize this collected information. After drawing the data flow diagram or something similar, we identify the threads, and those threads can be one of the 6 categories mentioned here. We can document those threads that we identify, and we also know because there is a standard thread modeling process, so these threads are now standard, and there are standard security controls or guidelines to define like how we can prevent those threats. So we can identify threats. We can also then we know that okay, how to prevent those threats. Typically, the process of threat identification involves going through an iterative cycles where initially all the possible threats in the threat list that apply to the component are evaluated. At the next iteration, threats are further analyzed by exploring the attack paths, the root cause for the threat to be exploited, example vulnerabilities. And here on this slide, the vulnerabilities are depicted as orange blocks. And then there are necessary mitigation controls, the counter measures, how to overcome those, and those are shown here in green blocks. This is a stride threat modeling process, and it is a time consuming, and its success depends on how good the information is collected, how is the data flow diagram prepared, how good is the visualization, and then how we identify the threats. But it's a good way if the team lacks security expertise. There are other methods, but stride is the most well established. We can take this further. We can rank the threats from the perspective of the risk factors by determining the risk factor posed by the various identified threats. It's possible to create a prioritized list of the threats to support a risk mitigation strategy, such as prioritizing the threats to be mitigated first. We can rank each threat from 1 to 10 on all 5 of the assessment criteria. So this is a Microsoft Dread Risk Assessment Model. It gives us 5 assessment criteria, and for each thread we can give it some ranking on all these 5 from 1 to 10, and then we add the scores and divide the 5 by 5, and the result is a numeric score between 1 to 10 for each thread. Highest score indicate most serious threat, which we would like to mitigate first. The purpose of countermeasures identification is to determine if there is some kind of a protective measure, example, security control or policies that can prevent a threat from being realized. Vulnerabilities are then those threats that have no countermeasures. While Stride looks a system from the attacker perspective, there is another ASF and ASF categorization that is more a defensive perspective. And since Stride is time consuming, we can directly implement the countermeasures for each threat type defined in ASF, and these are the important ones to handle. So ASF defines 8 type of threats, and they also provided countermeasures. These 8 are the most popular threat types, so we can directly implement the countermeasures defined for these 8 type of threats in our applications. And then we can do some selective stride threat modeling. Particularly if we know we know many of the countermeasures, and if we have the ASF as a reference document, then we know what countermeasures we need to apply. And we can just look at the solution architecture or the application architecture, and then look from which countermeasure we need to apply. So ASF threat types and resolutions provided is a reference. We can overlay the security architecture on the top of the solution architecture, like in this example. Everything in this dark gray color is a countermeasure that I have applied on the existing architecture. Till few years, I was in solution architect role and I gave interviews. I also took more than 100 interviews for solution architect roles. And there are a few more good topics which are asked in the interviews, like OAuth, OpenID Connect, TLS, what kind of security we need for APIs, especially now since we have GraphQL, which is different from method-based security technique we discussed a few slides back. And then symmetric asymmetric encryption, how we apply security at the different lifecycle stages of the software. And especially now since we have cloud, most of the things are on cloud, so we need to understand what the security features are from the cloud perspective, or if we are migrating something from on-prem to cloud, then what we need to take care. Thank you very much. If you like the video, then please like and subscribe to my channel. Thank you.